Hi everybody. We're going to take a moment here to look at the solving the unit problem for the small word unit. I've made the table here that's in your book. You may want to open up your book to this page so you can see it better. I've added a column that has time with the assumption that year 0 is in 1650, as you can see. And we know from class that using an exponential equation is the best way to model population growth. So that's what we're going to start with here. We're going to start with an exponential equation. We know that the general equation is y equals ab to the x power. And we have two parameters in a and b, which means we need 2 points. So the first model I'm going to make here is going to take the first and the last point. So basically 0, 470. And remember, that's in millions of people. And the second point is going to be 345 for time and 5730. That's also in millions for population. Immediately we can see here, without doing any calculations, that our initial value is 470. So our equation looks now like 470 times b to the x power. We need one more point so that we can find the parameter b, and we'll choose the second point here and substitute the values for x and y in. So 5,730 equals 470 times b to the 345th power. That's a pretty big power. Undoing this equation here starts with dividing by 470. So I get 5,730 over 470 equals b to the 345th power. Now recall, this is not an exponential equation. This is a power function. So we are going to, rather than apply any logs, we are going to, I guess you think of it as taking the 345th root. Most of you know that I prefer using fractional exponents. So we're going to raise both sides of the equation to the 1 over 345th power. And when we do that, we are going to get 5,730 over 470 equals b to the 1 over 345th power. Now, solving for this, in your calculator, you would have to, oops, sorry, I forgot to do this. It looks like my screen's messing up. Taking this fraction and raising it to the 1 over 345th power, over here will give you a b value of approximately 1.00727. That's 0.727% growth. And our model, therefore, in its final form looks like y equals 470 times 1.007 to the x power. Model number 1. Okay, so with model number 2, what we're going to do here is choose 2 different points to create our equation. Remember again, where y equals a b to the x. This time I'm choosing 2 points that are closer in time to where we are in this current year, which are 1990 and 1995. So that means the 2 points I'm using are 340, 5290, and 345, 5,730. We've got this equation. We substitute our values in for x and y to come up with 2 equations, and we have a system here. I'm going to use the first one here, 5290 equals a b to the 340th power, and 5,730 equals a b to the 345 power. And in this case, when we're solving an exponential system of equations, rather than doing something like elimination, we have to divide both equations. I recommend that you always start with the b exponent that has the higher number with the numerator. So that would be ab to the 345th power over ab to the 340th equals 5,730 over 5,290. That's my recommendation. It is not something that you have to do. You could do it the other way around, the reciprocal of that, and you would still get the right answer. It just takes a few more steps. On the right side of the equation, the a's cancel out, so you're left with b over b to the 345th power and 340th power in the denominator. On the right, you carry down the ratio here. And what this ends up doing here is simplifying quite a bit, because our exponent rules say we can subtract the exponent in the bottom there. And we end up with b to the 5th equals this ratio. Again, this is a power function. It is not an exponential function, so we raise both sides to the 1/5 power. And when we do that, we get b to the 5th to the 1/5, which equals b, equals our ratio, populations to the 1/5. Put this in your calculator, and you get, for this particular model, you get b is equal to 1.0161 approximately. That is a 1.61% growth. And the model looks like y equals, oh, we haven't gotten a yet. So now we have to take this value of b and substitute it back into one of our initial equations. So what I'm going to use is the second equation. So 5,730 equals a, and substituting my value for b gives me that, and the x value that goes with that y value is 345. Dividing both sides by our exponential number gives me this. And if I put all that in my calculator, I get a is equal to approximately 23.12. And remember, that's millions of people. So coming back up to my, where I started off here, I'll do it again. Y is equal to 23.12. That's my a value, my initial value, times my base, which has the growth rate hidden inside of it, to the x power. There is my model for using those last 2 points. So let's summarize and compare the two models. On the left is the model where I used the initial point in 1650 and the end point in 1995. And on the right is where I used the last two data points in 1990 and 1995. And so what we can see here is they have quite a few differences, and they're trying to model the same data. The initial value, you can see, is very different. Which one's better? This is a little subjective. You could say Model 1 is better because it's closer to the beginnings of when people started to immigrate out west. Again, that's subjective. The growth rate is ginormously different, 0.7% versus 1.6%. Which one's a better one? Well, you might argue Model 2 because it's closer to the modern era of growth rates, whereas back in 1600s, that growth rate was, very small and not sustained. Again, it's subjective. You can make arguments for or against each. So let's take a look at what this really looks like graphically. Here is the data plotted from the book. And you can see it does model an exponential growth as you plot those values. Let's see how our equations that we found and are meant to model this stack up. So first, let's take a look at model number 1, which is going to come up in blue. That's our value with 470 as our initial value. That's our equation that has 470 and our growth rate of 0.7%. And that is not probably the best fit. You can see it does go through the first point at t equals 0 and the second point where t equals 345. But really none of the other points are caught by that blue line. So maybe that's not the best model. I don't know. We'll see. Let's take a look at model number 2. where we had a 1.61 growth rate. This is in red. That's interesting. You can see towards the end of the graph, meaning the last points along the x-axis, it does seem to fit quite nicely. But at the beginning, it's really, really far off. So particularly at t equals 0, it doesn't even come close to that value, which of course we knew already. Let me overlay both of these graphs together. You can kind of compare them visually. So you might say, well, what could I modify these equations to better fit the data? And so here we start talking about transformations, which we talked about quite a bit in the unit this time. And that is, can we add values to y? Can we add values to the x to horizontally translate? Adding values to y, you know, means a vertical translation. And so you can see I've got a model here where it's going to come up in green. I've added 300 to my y value for my second model, the red model. And so the green is showing a vertical shift up by 300. That'd be 300 million people. To try and get us a little closer to, on the left side of the graph, a little closer to modeling the actual data that happened over here in 1650 and 1750 without sacrificing too much of the accuracy we got at the end back in the the mid to late 1900s. So a vertical shift did seem to help a little bit. Although you could then argue that some of these values here at the beginning of the 1900s now are much less modeled, much less accurate in their model. But if we had a lot of time, we could start to play with these translations by adding to the y values or possibly adding to the x values to see what would happen there. Maybe I should try that right now. Let's take a look at taking y2, which is our second model, and possibly let's shift it right by, let's say, I don't know, 50 years, and then see what happens there. This is going to come up in light green. That was not particularly good. That went very far away, but maybe if I just add or subtract 10, shift it to the left 10, and that's not bad. Maybe I could come up with a better color here, maybe purple, so we can see it. Get rid of some of this other stuff. And you can see now we've taken the red graph, shifted it to the right a little bit. Still doesn't really model the beginning values much, but let me add that 300 back into it for our purple model. And, that seems to do quite well. So these are ways you can start to play with your model to try and make it better fit the data. You won't have a perfect model. There's just really no way that that's going to happen, but that's reality. That's what data does in the real life. You come up with the model that best handles and treats the situation, and then you go with those numbers. Thanks for listening. I hope you enjoyed this unit, Small World.